In this video, we're finally going to use everything that we've learned in the course. And we're going to learn how communication systems actually work and figure out the basic elements of communication system design. First, let's recall what the fundamental model of communication is. There is a message that someone wants to send to some destination, and the problem is that doing that is not easy because of the channel. Nothing good happens in the channel. Signals get attenuated, sometimes filtered, there's noise, interference, all those kind of issues pop up. So to best combat how the effects of the channel has on transmissions is that the transmitter and receiver are there. There are systems which produce signals related to the message, which makes it easier to get the message through the channel and to bring back the original message as well as possible. Like I said, we know all the tools already to figure out how transmitters and receivers work. They involve modulation and filtering, and we already know how to do that. The thing we need to learn is so we can figure out which tools to use are the characteristics of the channel. That governs everything. We need to understand the structure of the message and the channel. Well, in this video we're going to talk about the wireless channel, electromagnetic radiation, and we're going to see that it has several interesting characteristics, both good and bad. Okay, so everything in the world of antennas, wireless communication is governed by Maxwell's equations. And here I show them. We're not going to talk about how to solve them for any particular setup. What I'm more interested in are the properties of Maxwell's equations, and that's what I want to talk about. So, interesting properties. First of all, those equations are linear. That is very, very important. So the idea is that suppose there are two transmitters, one sending a signal S1, another one sending signal S2, and they're coming out of these two antennas. And here we have our cell phone sitting down here. What that antenna gets on the cell phone is it's going to get both signals, and it looks like superposition. So what you're going to get are both signals. Now it could turn out that it's the transmitter sending signal 1 is what the cell phone person using this cell phone really cares about. However, S2 is going to come in also. So the idea is, how do you block this signal you really don't want? Well, the signal you don't want is called interference. Interference is primarily produced by humans. It's not necessarily a natural phenomenon, although it could be in some cases. So we have to figure out how you design the communication systems as a whole so that the receiver can figure out what's coming in and pull out the signal it wants. Well, okay, there's another side to the linearity thing, and that is, suppose again S1 is trying to send a signal to that cell phone. Let's suppose the second antenna is trying to send a signal to that cell phone. Well, they're going to pick up both. S1 is going to be picked up by that cell phone, and S2 is going to be picked up by that cell phone. So the upshot of this is no privacy. Once you send a signal over an antenna, a wireless signal, any other system that has an antenna can pick it up. So this means you have to be a little bit careful if privacy is a concern about how you send that message. Okay, so another thing that's important is that waves, electromagnetic waves, propagate at a speed of c. So let me illustrate what propagation is. Suppose I draw a axis It's a little interesting. Suppose this is space and this is time. And at some particular location, I send out a pulse that's of this width in time. What propagation means is that sometime later, that same pulse appears at a different position x. So the distance here, let's call it delta x, and the difference in time, delta t, the speed of propagation is delta x over delta t, whatever that may be. Well, for wireless signals, that speed of propagation is the speed of light. And if you go back to Maxwell's equations, it's given by 1 over the square root of epsilon mu, and we're not going to go into the details of how that's calculated. But in free space, the well-known result is that the speed of propagation is 3 times 10 to the 8th meters per second. That's the number we're going to use for wireless systems. Now there's another aspect of propagation that applies for sinusoids. So let's suppose I have a time axis and I have a sinusoid that's coming out of an antenna, so it's propagating. So this time difference is that's the period, and we know that's 1 over f from all we've already learned. However, I can also plot this as a function of space. Same signal because it propagates. And now the period in space is called the wavelength lambda. Lambda has units of distance. And it turns out for propagating waves, the wavelength times the frequency is equal to the speed of propagation. Very important result to keep in mind. So suppose we do a little example here. Suppose we have a frequency of 1 gigahertz. And that's 10 to the 9th. So that gives a wavelength of 0.3 meters, which is 30 centimeters. So the wavelength is still pretty significant compared to the size of your cell phone if it's communicating at a frequency of 1 gigahertz, which is pretty close to what is used these days. Now another less understood result is that because of Maxwell's equations and the properties of the atmosphere and other things, and the properties of antennas, is that low frequency waves do not propagate well at all. In fact, as we'll see a little bit later, the United States government does not regulate the transmission of signals below about 10 kilohertz. You can do anything you want. So if you try to send an audio signal from one place to another directly using an antenna, it's not going to work very well because it has no range. The low frequency waves just don't propagate. So in wireless systems, somehow we have to shift the frequencies of the message signal up to higher frequencies so they do propagate well. We'll see how that works a little bit later. All right, more properties. And there's the conservation of power issue, which means that the amplitude of a signal transmitted by our wireless has to decay with distance from the transmitter. So here's a little diagram. And here we have an antenna that, let's assume, sends out a short pulse, just for fun. If you look at a specific distance r, let's say that, from the antenna, the power, if you integrated the power over that sphere, right, we're in 3 dimensions here, that has to be the total power radiated by the antenna. If you go out a bit further, that power cannot be unchanged. We're essentially assuming that the wireless medium is lossless, so there can't be a power change. However, this is a bigger surface area out here than in here. Consequently, the power at a given distance from the transmitter has to go down. We must have the result that the power at any given distance from the transmitting tower times the surface area of the sphere has to be a constant. So that leads to the fundamental result that the power at a receiver gets must obey an inverse square law. So the more distant the receiving antenna is from the transmitter, the smaller the power is going to be. Or maybe said a little better, the amplitude has to go down like 1 over r. Okay, it's the fact of life, fundamental physics. Now, the other thing is that materials, both common and natural, can absorb and reflect waves. And this depends on their characteristics. So let's suppose we're in a city environment now, where we have tall buildings, and here's a radio tower trying to send a radio signal to my little car down here. Well, if there's a direct path, that's fine, but it turns out these buildings can reflect, in most cases do, buildings and cities do reflect the electromagnetic energy, and actually this antenna will see both the direct and reflected paths. This turns out causes a little bit of problem in communication systems. More importantly, suppose there's another vehicle over here, which I'm going to draw very badly, which is trying to receive the same signal. Well, that signal is blocked by the buildings, and this antenna won't receive anything. This is why driving in cities, cell phone signals and radio signals can go in and out depending on the height of the buildings and how many are, where they're positioned, where the transmitter is. It's a real problem. Well, it also turns out natural entities can also affect electromagnetic transmission. And I'm thinking here of a tree, and you may wonder, why would a tree block a signal transmission? And the reason is because the leaves are loaded with water. That's their primary constituent. And water is a very good conductor of electricity, and essentially the tree shorts out the electromagnetic transmission, and our poor little car here, the only thing it can get is a signal by a reflected path. So if you're going through even a rural area where there are lots of trees, you can have your transmission sorely affected by trees and other naturally growing things. Now, let's talk about that direct path a little bit more. And here we have what's called line of sight communication. And that means that the transmitting receiver antenna and the receiving antenna can, quote unquote, see each other. That's why it's called line of sight. There's a direct, straight line path connecting the two. Because of the curvature of the Earth, this doesn't go on forever. If you're over here somewhere, there is no line of sight path to this receiving antenna. In essence, you cannot send a signal directly from this transmitter over to the other one because the Earth gets in the way. So it's very interesting to know what is the line of sight transmission distance. Well, simple geometry using the Pythagorean theorem, it's pretty easy to derive, shows that the line of sight distance is given by this formula, and this is the radius of the Earth. So let's suppose we have a little example here. Suppose we have a 100-meter tall antenna. It's a pretty tall antenna. And you can plug it into the formula just as well as I can. The line of sight distance is about 71.5 kilometers. Now that's the total distance here. If you were on the ground level, let's say holding your cell phone, then that distance, let's say from here over to from the transmitter is going to be half of that. So 35 or so, 37 kilometers is the total distance that a cell phone can be reached by a 100-meter tall antenna. So it's pretty limited, and certainly not small compared to the circumference of the Earth. This was a big problem when they were trying to develop transoceanic communication, and Marconi was trying to figure out how to send wireless telegraph signals across the Atlantic Ocean. Well, it turns out he did this experimentally, and it turned out it worked because he discovered and quickly was explained that there's an ionosphere up there, which really helps. So here's my Earth, and let me complete the circle as well as I can. And suppose I'm over here and I'm trying to send over here. Well, there is no line of sight path. It's too far away. What was discovered is that the ionosphere acts like a mirror. Signals can come up and be reflected back down to Earth, enabling communication between distant places. Now, I deliberately showed it over here as being a little iffy, and that turns out to be true. It turns out at some frequencies the ionosphere is transparent and radiation goes straight through. At other frequencies it acts like a mirror. And so you have to understand the frequency properties of the ionosphere. It's similar to a transfer function. This is more of a reflectivity function that's a function of frequency. And there's another phenomenon, and that is that the transmission reflection characteristics depend on the time of day. Turns out solar radiation from our sun interacts with the ionosphere, and during the daytime it does not look much like a mirror, those same frequencies, where at night it looks like a mirror. And I don't know if you've ever tried this, but at night using classic AM radio, you can receive stations from a very long distance away. However, if you tune into that same station during the daytime, it's impossible. You will not receive it at all, and that is because the ionosphere changes its characteristics depending if it's the sun is sending radiation to it that affects it or not. Well, how about satellite communication? Now here, almost drawn to scale. The idea in satellite communication is that suppose there's a transmitter here, and here's our little satellite up here. And the way satellite communication works is that a transmitter sends a signal up, and that gets re-radiated back to Earth, and basically has a coverage, basically about a third of the Earth's surface, let's say. Well, now as the Earth rotates, okay, what you want for the geosynchronous orbit is that it rotates a greater distance, but in the same time. So again, it appears that by the time the antenna gets over here, our little satellite is directly overhead still. So you don't have to change the transmitter at all. That's called a geosynchronous orbit. And so what happens in a geosynchronous orbit is that the time it takes to go around once has to be exactly 1 day. And when you do the physical calculations from Newton's equations, what you get is that means that the radius of that orbit from the center of the Earth has to be 42 million meters. That's a long, long way. And in fact, it turns out there's a significant time delay. If you take the speed of light and try to figure out what the time delay is, the time delay in sending a signal up to the satellite and back is at least about 1/4 of a second. And if you have to do this several round trips. So to get around the Earth, let's say, that it's just going to add. And so that's the big delay that you encounter in satellite communication systems. I know in the old days when you used to have a telephone call to places like India from the States, they used satellite communication, and it greatly affected the quality of conversation. The delay was instantly noticeable. Very interesting. So anyway, those are the characteristics of wireless channels. There is just from fundamental physics, inverse square law governs the power that a receiver and receiving antenna can get from a transmitter. And speed of light may be fast, but it's not infinite, and you can get significant delays between transmission and reception. Depends on distance, of course, and this really affects the satellite communication scenario. More importantly, Maxwell's equations are linear, and superposition applies, which has, as I pointed out, good and bad properties. No privacy, but this enables broadcast, so one radio antenna can send to lots of receiving radios. However, radio is now faced with the fact that all the other stations are sending at the same time. You somehow have to get rid of the ones you don't want. And if you think about it for a second, what this means is filtering. We'll talk about that a little bit later. And the big downside in wireless channels is that lots of interference is possible, and it's all because of the linearity and superposition principle. We're next going to talk about wireline channels, and you'll see that the characteristics are very, very different.